Welcome to the fourth preparatory video for the IQB workshop, Python for Chem Informatics Driven Molecular Docking. And in this video, we're going to be looking at molecular similarity. And so I'm going to go right to the notebook for this. And we're looking at molecular similarity and molecular descriptors. The questions we're going to address are, how are molecules represented on computers for chem informatics applications? How can I measure the similarity of two molecules? How can I find out if a molecule contains a particular substructure? The objectives are to learn about graph representation of molecules, to learn about molecular fingerprints, and to use RDKit to measure molecular similarity. Now, we use chem informatics for molecular discovery. The writing here is really very good. I think I'm just going to read it. For example, you might want to process a large number of molecules to find molecules that are similar to a target, or that contain a particular functional group. But how can you tell if two molecules are similar? A chemist looking at two molecules might be able to make a judgment based on their chemical knowledge. However, when dealing with a large number of molecules, this problem becomes quite intractable. There are ways to detect molecular similarity on a computer that allow fast comparison and processing of molecules. Now we're going to talk about graph representation of molecules. Graph theory in mathematics is the idea that you have structures that contain nodes and that contain edges. And so here is a mathematical graph, and we have 6 nodes. Each of these nodes represents a point or a vertex, and each of the lines is called an edge. Now, as a chemist, you can probably imagine moving from this idea of graph theory to a molecule as a graph. And so in a molecule as a graph, the atoms would be the nodes, and the edges would be the bonds. And if you want to know, is it a single bond or a double bond, you can change the weight of those edges. Now, one of the things we try to do in using chem informatics is what are called substructure searches. So a substructure search is when you look in chem informatics to see if some pattern is found in a larger molecule. So for example, here we see a benzene ring, and we have aspirin, which is a larger molecule. If we look in aspirin, we can see that aspirin contains a benzene ring. All right, and so we would say that the substructure is matched here. And with graph representation and graph theory, we can do this within RDKit. And so RDKit can look for one smaller molecular graph inside a larger one. This concept is called subgraph isomorphism, and there's a link here to a presentation that can tell you more about that. At this point, if you're feeling a bit overwhelmed, keep in mind you don't have to understand everything about graph theory to do this, to do a substructure search. As a chemist or a biologist, you can look at these organic molecules and look for similarities by eye, but if you want to compare 1,000 molecules, you need to use a computer to do that. So we're going to be working with RDKit again, so I'm going to install it. And once again, I'm on Google Colab. So I just hit the run button here, and it takes a few seconds. It's going to start the installation process. While we're waiting for that to happen, we can talk a little bit about substructure matches within RDKit. All right. And so if we move to RDKit, we want to use the smile string for caffeine. So we can either go to PubChem to get that, or actually it's right here in the text. So I'm going to grab it from right here and copy that. I'm going to paste it in between those quote marks. Now notice we have single quotes here. It could be single quote or double quote. As far as I know, those are interchangeable in Python. It doesn't really matter, just that they match. Now, the next thing we need to do is we're going to look for a carbonyl group within caffeine. And so we need to have the smile string for a carbonyl group. Well, a carbonyl group is a carbon, so we'll make that a capital C. double bonded to an oxygen. A double bond is the equal sign and a capital O that gives us the carbonyl group in a smile string. Now we'll see that this falls short in a little bit, but what we do then is we insert here in the parentheses, we have matches equals caffeine dot get substruct matches. So that's a method in RDKit. And we're asking it to match the carbonyl, which is the group we identified here. And so when I run this cell, what we see is a caffeine molecule with the C double bond O, two C double bond O groups matched here. All right, so that worked pretty well. Well, let's now move on to another attempt. So what we want to do now is we want to look for methyl groups in caffeine. Now we can look in the structure here and we can see that there's a methyl group at this nitrogen, a methyl group attached to this nitrogen, and a methyl group attached to this nitrogen. So what I'm going to do is I'm going to go in here. I'll put the string for caffeine in again. That's a smile string. And for a methyl group, well, the smile string for a methyl group, we saw that before. The smile string for methane is just a C. All right. And so now we're going to ask it to do a match. Look in caffeine, get a substructure match for the methyl group. So we'll just say methyl here. And methyl's going to draw on the RD kit mole object based on the single carbon. All right. And when I run this cell, scroll down, and what we see then is it identified, this substructure search actually identified the three methyl groups, but it also identified all the individual carbons in the structure. So this approach doesn't work. And so for this substructure search to work, we need to do something different. The thing we're going to be doing different is we're going to use what are called SMARTS strings. SMARTS stands for Smiles Arbitrary Target Specification. So that's a pattern matching language for specifying substructures in molecules. It's similar to SMILES, but it's not the same thing, and it enables us to specify substructures with greater detail. So for example, instead of using a simple C to represent a methyl group, we use a CH3, but it will be in square brackets. That's one of the rules here. So this is a carbon with 3 hydrogens bonded to it. And so instead of using this chem mole from SMILES with a C, that highlights all carbons in the molecules, we just want to highlight the methyl groups. We can do that with a SMART string. So we're going to come back here once again and put in our SMILE string for caffeine. And in fact, you're probably thinking, well, you could have just used caffeine that you used above. That's true, because it's exactly the same thing. And now I'm going to copy this SMART string. Now notice the term here. We say methyl underscore pattern, and that's going to equal to chem. So we're drawing on the chem sublibrary of RDKit. And we've seen mole from SMILES before. Now we have mole from SMARTS. And so here we're going to place this term. So this is a CH3 group within square brackets in the quotes. All right. And so that's going to be the methyl pattern. And now what we're going to do is we're going to look for this methyl pattern within caffeine. So the same command we used before, caffeine.get substruct matches. I'm going to put in methyl pattern. And notice Colab helps us here. I can click on methyl pattern. And so now I have the full statement where I'm looking for matches within caffeine. So caffeine is the mole object we're looking for the matches in. We use this command get substruct matches. And the pattern we're looking for is methyl pattern, which we've defined here. And so when I run this, what we see now is caffeine, and only the 3 methyl groups on caffeine are highlighted. All right, so this is more specific. So for an exercise, I'd like you to pause the video at this point and look in the next executable cell. For this exercise, you're going to take a look in aspirin for the benzene ring in aspirin. Unless you know the SMART strings, you need to go to a linked page, which is linked right here to find that string. All right. So I'm going to pause here. All right. So the first thing I'm going to do is I'm going to open that page, the daylight.com page that has the smart strings on it. We'll come back to that in a minute. Now we need the smart strings for aspirin. I'm sorry, the smiles string for aspirin. So I'm just going to go to PubChem. And this actually takes me back to the page I was on in the previous video. Instead of tyrosine, I'll type in aspirin and do a search. And once I've done the aspirin search on PubChem, we see the smile string here listed. So we go in there. I'm just going to highlight that, and I'm going to copy that. We'll go back to our Colab notebook. And so I'm going to put the smile string for aspirin right here. So I'll just paste that. Well, let me paste. I'll do the Command V. All right, so I just pasted the smile string for aspirin. And so now we want to, actually, we're not looking for the benzene ring in aspirin. We're looking for the carboxyl pattern. All right, so we go back to this Smarts Examples page. And what I'm going to do here is, rather than scroll down the page, I'm going to just do a search. I'm going to say carboxyl. And we have a number of things here, but these are too general. We want to get to the point where we actually have a carboxylic acid. So I scroll down here, and here is carboxylic acid. And so here's the smart string, and notice it has square brackets on either side. So I'm going to copy that. I'm going to come back in here, and I'll place a smart string for the carboxylic acid group right there. So we have then, this is called carboxyl pattern, and we're using the chem sublibrary again, chem sublibrary of RDKit, the dot, and that we're calling the method mole from smarts. And here is our carboxylic acid pattern. And so I'm going to go down here and look for matches in aspirin. With that same function, get substruct matches. I start typing carboxyl, and Colab tells us, oh, carboxyl pattern is one of the options you want, or is the option you want. So what I'm going to do now is I'm going to hit the run command, and the substructure match will be done, and then aspirin will be displayed with that. So we hit that run command. And here we see aspirin with the carboxylic acid group highlighted. Now notice it highlighted the carboxylic acid group, but not the ester function. So it's a distinct pattern match. So that's just a little bit about matching using smart strings. We're going to move on now to molecular fingerprints. All right. And so what happens with a molecular fingerprint is you look at a molecule and you define that or describe that molecule as a series of zeros and ones. And these fingerprints are built by considering the molecular structure, often from the graph representation. And there is an algorithm that's used to create a vector. And in the end, we're going to end up with a string that has zeros and ones. And the more intricate a molecule is, the more ones it's going to have. A simple molecule has mostly zeros. All right, you can learn more about this from the Chem Informatics course on Chemistry LibreText. And what we're going to be doing here is we're going to be getting the RDKit fingerprint for caffeine. All right. So what we need first of all is we need the molecules for or the smile strings for aspirin and benzene. So I'm going to go up here, and this is the smile string for aspirin. We already have that, so I'm going to copy that. And we're going to paste that right in here. So we have aspirin equals chem.mole from smiles, and then the smile string for aspirin. All right. Now we want to do a smile string for benzene. Now, you can look this up on PubChem, but if you think about it, benzene's a 6-carbon aromatic ring. Aromatic means you use lowercase letters, and it's a ring, so you have to have a number in there. So C1, that's our first carbon, and then 1, 2, 3, 4 more carbons, and then another C1, and that gives us the smile string for benzene. So what we're going to do now is we're going to develop the aspirin fingerprint, and we're going to ask allchem. Now notice we say from rdkit.chem import allchem. So this is another subgroup of rdkit that contains the fingerprint functions. And so aspirin underscore fingerprint equals allchem.rdk fingerprint, and then the variable here is aspirin. And so what's going to happen is we're going to generate that, and then we're going to find out what's the type of this variable. So the type of this variable is an rdkit data structure, an explicit bit vector. Okay, I'm not going to try to explain what that is, but in fact, one of the ways that we can work with a fingerprint is we can convert it to a bit string. And so if in the next cell, we're just going to execute this cell. You don't have to do anything to it. And so we take this aspirin fingerprint, and we're going to convert that to a bit string. To-bit string is a method, so you have to have the open and close parentheses after it. It can be empty. So I did that, and you can see we've got a long list of zeros and ones. And there are quotes before and after that tells it that this is a string. All right. So if we want to make a benzene string, we'll see a string of the same length, but with fewer bits set. What that means is we'll have fewer ones and more zeros. All right, so what we're going to do for the benzene fingerprint is we're going to insert the variable that represents the benzene mole object here. So we just type in benzene. And we created that a couple cells above. And then we're going to create a benzene string using the same exact command we used for aspirin on the benzene fingerprint. So the to-bit string method. And then we're going to print that so you can see what it is. And you can see if you look at this, that it's just, for some reason, it shows, rather than curling around, it shows as a long string. And there's just a few ones in there. If you compare that to what we saw with aspirin, the aspirin fingerprint, lots of ones in the aspirin fingerprint. So we can actually do some analyses, including a substructure search with these two bit strings. All right. And we've actually already done this, but I'll do it again. So we're going to generate the aspirin string. Actually, we haven't. All right. So we did, we said we had fingerprints, but we didn't actually, we printed the strings, but we didn't save those strings to variables. That's what we're doing here. So we're going to save the aspirin string to a variable, and we're going to compare it with the benzene string. All right. So we want to compare it. The benzene string is I don't know if these might be 2024 characters long. I don't remember exactly what the number is, but what we want to do is we want to find out how long that benzene string is. We want to compare that benzene string one position at a time with the aspirin string. And we also set a variable, we'll call it matches, and we'll say it's equal to 0. And so we're going to do a for loop. We've done this before. And in the for loop, we're going to go for I in range of num bits. So num bits is the length of that benzene string. So we're going to go one character at a time down the benzene string. And what we're asking is if the benzene string position I is equal to 1, and we see this up here, you can see a little bit, I don't know, 50 characters in, there's a 1 there. All right, so if the benzene string sub I is equal to 1, now notice this is a logic comparison, and we're going to print something. Now we need to have a Boolean comparison here for the aspirin string and the benzene string. So what we're going to do is type in aspirin string, ASPIRIN, and once again, it's good to click here to get what Colab offers so I don't make a typo, but I have to compare one character at a time. So I'm going to say I here. Then I have a comparison term. So if aspirin string is equal to benzene string, so we grab benzene string, once again, sub I. So we're comparing those, and if the benzene string at position I is equal to 1, and we're then checking to see if the aspirin string at that same position is equal to 1, because it's equal to the benzene string at that position, And what we're going to do is anytime there's a benzene string position that's equal to 1, we're going to increment the counter here. And the way we do that is you just type in plus equals 1. So that's just going to increment the counter, all right? And now what's going to happen, I'll give you a minute to look at this string because you haven't seen this before. What's going to happen here is every time there's a match, it's going to print a value of true here. If in fact there's a 1 in the aspirin string position I that matches the 1 in the benzene string position I. All right. And so then we've got an F print statement here at the bottom that says print F, quote, there are matches. Now remember, this is a variable, so in an F string or an F string, we have to put that variable inside curly brackets. There are matches positions where the benzene fingerprint matches the aspirin fingerprint. So when we run that, you can see that we get the word true 12 times. And a statement here, there are 12 positions where the benzene fingerprint matches the aspirin fingerprint. So that's how that cell works. And if this went a little too quick for you, I'd encourage you to pause the video here and to look through that code again and to recognize that the true statements reflect the fact that at these positions where the benzene string position I has a value of 1, the aspirin string also has a value of 1 at those positions. And the matches plus equals 1 gives us a count of what's going on there. So we're just comparing those fingerprints. Now, there are other ways to measure similarity. One of the chem informatics tools we use for similarity is called Tanimoto similarity. And we can calculate it, the Tanimoto similarity between two molecules, A and B. We match the fingerprints for those two molecules, and A intersect B. So the A with this shape above it says the intersection. So this is where both have a value of 1 or a value of 0. So where they match. And A plus B is the sum of all the 1 bits in A and B. So that's here. Minus A intersect B. So we're trying to distinguish those. So these are the unique 1 bits across both fingerprints. And so this is the Tanimoto similarity. It's going to have a value between 0 and 1. And so what we're going to do in the next cell is just run this function. You don't have to do anything except hit the run button here. And so in order to do this, we have to import a tool called data structs or actually a sublibrary from RDKit called data structs. And so we have data structs dot Tanimoto similarity. And then we compare the two fingerprints, benzene fingerprint and aspirin fingerprint. We run that, we see that the similarity is not very high. It's 0.0338 and so forth. All right, so it's pretty low similarity, but there's some similarity between the two molecules. So what we're going to do now is an exercise where we go further with this. We're going to measure if benzene is more similar to pyridine or to aniline using the RDKit fingerprint. All right. So what we'll need are the SMILE strings for aniline and pyridine. We've already got the SMILE string and the fingerprint for benzene, but we go to PubChem. So we're going to get the SMILE string for aniline and put it in this position. So if we click on the link for PubChem, I'm going to go in here and type in aniline, A-N-I-L-I-N-E. Scroll down the window to find the SMILE string. It's right here. I'm going to copy that. I'm going to come back here. I'm going to paste that SMILE string for aniline right there. And we want the SMILE string also for pyridine. So I'm just going to go right back to PubChem. Type in pyridine. Oh, my fingers are clumsy this morning. All right. And here's the molecule pyridine. And here's the SMILE string for pyridine. So I'm going to type that in here. So now, if I want to generate the fingerprint for aniline, I'm just going to put the variable aniline in here. Now remember, when I type in aniline here, that actually represents, that's the RD kit molecule object, aniline. And I've typed in pyridine here. I start typing pyridine, PY. It comes in and says, oh, let's put in pyridine. So now we're going to do a similarity between these two structures. And we're going to compare aniline and benzene. So I'm going to say benzene, comma, aniline. And this will calculate that. Now remember, we've got, oh, not benzene, benzene fingerprint. And likewise with aniline, it's got to be aniline fingerprint. We can't just do the mole objects. We have to have the fingerprints. All right. So once we have those, we can compare benzene and aniline. We're going to do the same thing now with benzene. We have a comma there, and pyridine. And once again, I'd like to pull these that are offered to us by Colab because it avoids me stumbling over typing properly. All right, so now we've got our statements here. The first two lines, we're creating RD-kit mole objects for aniline and pyridine. In the next two lines, we're creating fingerprints for aniline and for pyridine using allchem.rdkit fingerprint. And then we're going to use the Tanimoto similarity function to compare first benzene and aniline. And then we have an fprint statement. The Tanimoto similarity of benzene and aniline is, and then the similarity, once again, is a variable. We have to put that in curly brackets. And we do the same thing for benzene and pyridine. So when I hit the run button, we find that the Tanimoto similarity of benzene is 0.315 and so on. And for benzene and pyridine, it's 0.228. And if you think about this as a chemist, well, aniline has the intact benzene ring. Pyridine has an aromatic ring, but one of the carbons is the nitrogen. So it intuitively makes sense. Now, we've already looked at fingerprints. Fingerprints are examples of molecular descriptors. And so that is a numerical value that represents some property of a molecule. There are lots of other descriptors available in RDKit, and the descriptions can be varying dimensions. Some are zero-dimensional. Those would be a simple number like molecular weight or number of heavy atoms. Could be one-dimensional, so it could be a count of atom types or hydrogen bond donors or acceptors, or two-dimensional, and that would be things like fingerprints or graph representation. Three-dimensional includes polar surface area. I don't think we're going to get that far in the IQB workshop, but what we are going to do is we're going to bring in from rdkit.chem the descriptors, which is a collection of methods. And so if we want to determine the molecular weight of caffeine, we're going to say caffeine molecular or caffeine underscore mole underscore weight. So that's just a variable we're declaring. And we're going to say descriptors.molwt. And notice the capitalization is very specific. And so we need the mole, the RDKit mole object for caffeine. Well, we've already defined that well above. And so what we're going to do is we'll put that variable here, caffeine. And then we want to know what the molecular weight is. So I'm just going to say print caffeine molecular weight or caffeine mole weight, pull that off the list. When I do that, gives me a value of 194.194. And just to check, let's go to PubChem, type in caffeine, and caffeine is here, and the molecular weight is given here as 194.19 grams per mole. Now, it's possible to calculate all of the molecular descriptors for a molecule at once using calc mole descriptors. And we're not going to do that here. But one of the things that is often used with molecular descriptors is there's something called Lipinski's rule of 5. And that's a rule of 4. There's actually 4 different things we look at, and these relate to the number 5. So, and Lipinski's rule of 5 Lipinski came up with this rule when he was looking at things that would be orally available drug molecules. So he's a medicinal chemist looking at this. So he looked at the molecular weight, and according to his set of rules, the molecular weight should be less than or equal to 500 Daltons. The number of hydrogen bond donors should be less than or equal to 5. The number of hydrogen bond acceptors should be less than or equal to 10. And the log of the partition coefficient between octanol and water should be less than or equal to 5. And so in the next cell, what we've done is we've got a variable we're declaring MW for molecular weight, and we're saying descriptors. So we're calling the descriptors that we imported in the previous cell here, descriptors.molwt. And then we've already declared we have a mole, an RDKit mole object called aspirin. Okay, and in fact, when I highlight aspirin, you can see that above here it says rdkit.chem.rdkit.mole instance. All right, so we've already defined that variable. So we do that to get the molecular weight of aspirin. HBA is for hydrogen bond acceptors, and so the descriptor we use for that is NO count in aspirin. HBD is for hydrogen bond donors. The descriptor we use for that is NHOH count for aspirin, and then log P is descriptors mole log P for aspirin. So what we're going to do then is we set up some rules. So here's a list of rules. And so we got molecular weight less than or equal to 500, hydrogen bond donors less than or equal to 5, hydrogen bond acceptors less than or equal to 10, and log P less than or equal to 5. So we've set up those rules. When we do print rules, it compares the values of these variables with these statements. So these are comparison operators like we saw before. If I hit run here, then we can see that in the case of aspirin, it's true on all 4 counts. So according to Lipinski's rule of 5, aspirin might be a good, is going to be a good orally available drug. So let's do the same thing for insulin. Now, in order to do this, we need to have a SMILES string that represents insulin, and we're going to do the same exact functions we did above with descriptors. But first, we'll get the SMILES string. So I'm going to say insulin equals RDKit, no, not RDKit, chem, mole from SMILES. So notice, oh, let me show you that again. When I hit chem dot, it came up with mole from SMILES as it's showing in light gray. If I hit tab, it just accepts that. Then I'm going to put a parentheses there, and then I'm going to go over here to PubChem. Oh, that's funny. All right, so if I type insulin in here, and you know that insulin is a polypeptide that's pretty long. And in fact, if I look up insulin on PubChem, we get this great long string. But this is still a SMILES string that represents insulin. So I'm going to put that in here. Now it's important here, it has to be inside quotes. So very long inside quotes, but it's there. So I have insulin. I'm not going to visualize it. And so now what we want to do is we want to do the same thing we did in this cell. We want to get the Lipinski descriptors, but only in this case, instead of aspirin, we're going to do insulin. So I'm just copying those, pasting them in down here. I'm just going to type in insulin. Type in insulin again. And once again, let's use the tool that's available in Colab where it does it automatically, so I don't have to worry about typing errors. Those are annoying. Now, another thing to notice here is once I did this, if I go to the next line, then Colab says, do you want to do the same thing again? And in fact, I do. So I'm going to hit rules and use the same exact rules. Now remember the values we're going to see now for molecular weight for hydrogen bond acceptors, hydrogen bond donors, and log P is going to be different. They're going to be for the values for insulin. So if I hit tab, it accepts those, and it says false, 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 true. And the question is, well, why are they false and true? Well, let's take a look at that. So I'm just going to go here and I'm going to say print, and I'm just going to print those four variables, the values, so you can see them. So I'll do an F print statement, F, and uh, molecular weight. Oh, this is good. So I type print molecular weight, and it says it's going to give me the value, going to give me F print statements for all four of those things. So Google Colab figured that out. So I just hit the tab key, and now I have my four statements that's actually going to print what I want, except this is interesting. The last one didn't close properly. So I'll close the quote and then close the parentheses. Oh, it's doing the comparison here, but what I really want is just the molecular weight. So I'm going to take this out. I'm taking out the comparison terms. I'm just going to have it print the value of the variable so we can see what they are. So in this case, Colab anticipated that I wanted something, but didn't get it quite exactly the way I wanted. So if I go in there and I look at the molecular weight, it's over 5,000. So clearly that's much greater than 500. There are 88 hydrogen bond donors, 142 hydrogen bond acceptors. Log P is less than 5. In fact, it's dramatically less than 5. It's almost minus 20. So that's the end of this notebook. I hope you found it helpful. And there'll be one more notebook. Actually, it's going to be the E notebook.